Konstantin and the other organisers for the very kind invitation to attend this workshop and to speak. And also all the other speakers. I've really, not knowing half as much as most of the audience about water waves, I've really learned some great things this week and going to go back home with some great problems to look at. So thank you very much. So I really hope today to tell you about some other work, in fact, not this particular work, on compactons. Unfortunately, I'm not quite ready to talk about those results, especially on camera. So instead, I'm going to talk about another problem from water waves, which I hope will be just as interesting. And this is all joint work with Jeremy L.Marzuola, who's at UNC. So what sort of problems am I interested in? So I'm interested in, one of the things I'm interested in is looking at the long-time behavior or long-time dynamics of various dispersive model equations that arise as asymptotic limits of lots of systems, but in particular things like water waves. And so I'm sure everyone's very familiar with these kind of equations, things like the KdV, Benjamin-Ono, intermediate long wave equation, the NLS, KP type equations, so on and so forth. So these equations are very interesting in their own right. As somebody from dispersive PDE, these are sort of the canonical dispersive equations that display lots of the effects of dispersion that we might be interested in. But I also see them as a very good sort of sandbox or testing ground for developing powerful techniques we can then take from these more simple sort of semi-linear type equations and apply them to quasi-linear equations. And so today I'm going to talk about some techniques that were developed initially on semi-linear equations but have had some success with things like the water waves and capillary waves in 2D and 3D in fact. So the two main questions, and Alex Ionescu gave a very nice talk the other day explaining the kind of problems that we might be interested in. So problem number one is, are these things well posed? And in particular, do we have global solutions, or do these things blow up at some finite time? And once we could know something about the well-posedness, can we say something about this, either blow-up behavior or asymptotic behavior? And so this talk is going to be one of these cases of there are multiple ways you can skin a cat. I'm going to talk about a particular technique for proving particularly global existence and asymptotic behavior in some cases, but it's by no means the only method, but hopefully I can try and persuade you that this method has some benefits. Okay, so what's the particular problem I'm going to focus on? So as I said, this can be applied, or this method can be applied to a lot of different problems, but I'm going to focus on one particular one, which is a problem arising from internal waves. And so we've already seen this kind of picture before, so I won't go into too many details. But the idea is you have two fluids. The one on top is obviously less dense than the one beneath it. And in a particular scenario, we're going to be interested in long waves in the weakly nonlinear regime, and in the case where the top fluid is much thinner than the lower fluid. So people who know much more about these things came up with a model for this. So this was in work of Camassa and Choi back in '96. So as I said, irrotational flow, weakly nonlinear long waves, lower fluid much thicker, and they were looking at unidirectional wave propagation with weak transverse dependence. So these waves are propagating in the x direction, and there's some weak dispersion in the y direction, and you end up with an equation that looks like this. And if you stare at it for a minute, you'll realize it looks a lot like the KP2 equation. So here, I should explain what this operator T is. So this is the finite depth Hilbert transform that we heard about yesterday morning. It's also, I've seen it called the Tilbert transform. It's a sort of bizarre name, but does the job. And obviously, this is the inverse of the Tilbert transform appearing here. So this is a very natural two-dimensional version of the intermediate long wave equation when we're at finite depth, or the Benjamin-Ono equation when we take h equal to infinity. So when h is equal to infinity, the Tilbert transform becomes the Hilbert transform, at least formally. I'm going to talk about this equation on R2, but it, at least from a dispersive PDE point of view, is equally interesting on other domains. And actually, this is one of the questions I have for the audience, perhaps at the end, is which, if we're going to look at things like periodic solutions, whether periodicity in both directions or one direction is more interesting than the other. And this is certainly something that we're very interested in. Okay. So some other things that were worth saying about this equation. So it's a Hamiltonian equation. It's the Hamiltonian flow of this particular Hamiltonian and the corresponding symplectic form. And it also formally conserves the mass. So the Hamiltonian is maybe not a particularly useful quantity. It's not coercive, but the mass certainly is. And an interesting question, and one that I don't think there's an answer to yet, is are there other conserved quantities? So the intermediate long wave equation, the Benjamin-Ono, and the KP equations, of course, are integrable. And we should be a bit careful what we mean by integrable because they're infinite dimensional systems. So here I simply mean they have a lax pair, and they have an infinite number of conserved quantities, at least formally. I don't think it's known whether the Camassa-Choi system I had up before is actually integrable. I think probably the smart money is on it being integrable, but I don't think there's any lax pair or anything like that. Another thing that's maybe worth noting is for the nonlinear Schrödinger equation, or the KdV equation, say, the inverse scattering transform is very useful if you want to try and construct solutions. You can handle effectively arbitrarily large, smooth data, and this thing's going to work. All these nice conserved quantities give you Sobolev regularity, and in fact there's a continuum of conserved quantities that give you Sobolev regularity even at fractional indices. For the KP equations, this isn't quite true. So the KP inverse scattering transform is much less useful in that it can only handle small data in the first place. And on top of that, while the KP equations do have conserved quantities above the energy at higher Sobolev regularities, I think it's something like 2 or 3 energies above the Hamiltonian. The only possible solution that has has a finite higher order energy is the zero solution. So these higher order conserved quantities are kind of useless. But certainly whether this has some deeper structure is an interesting problem. Okay, so what I want to do now is sort of give some linear and nonlinear heuristics and give some idea as to why we look at this equation the way we do. So I want to start with the linear problem. So this is the linearization about 0, because this is, to all intents and purposes, we naively expect solutions to a first approximation should behave like linear waves, solutions to the constant coefficient equation. Here I've applied an antiderivative. So of course when you do this you need to fix the constant of integration somehow, and I've used this particular normalization which corresponds to a choice of the homogeneous Fourier multiplier of order -1. So using the Fourier transform we can write down the solution like this. So this SH here is my linear propagator, and omega h, or omega lower script h, is my dispersion relation, and this is of course pretty straightforward. And k here, I'm going to use it throughout, is just going to be shorthand for the frequency vector, two-dimensional frequency vector. Okay. So one of the things we can do once we have this Fourier representation is try and construct the fundamental solution. So all we're going to do now is take f to be the delta function, and we're going to plug that thing in, and we can write down what the fundamental solution is. So there are two interesting things to remark here. The first is First is this variable x plus 1 over 40 y squared that appears. So the fundamental solution really depends on these sort of parabolas, at least when time's non-zero. And this oscillatory integral itself, k, if you stare at it for a minute, you'll realize it's a half derivative of the fundamental solution to the intermediate long wave equation. Okay, so we have a fundamental solution, and one of the first things we can do with this is to get a dispersive estimate. So we can show that the fundamental solution has pointwise t to the -1 decay, at least when you throw in some of these derivatives. And so we get an L infinity, or a pointwise t to the -1 decay, at least for sufficiently integrable solutions, or initial data. And throughout I'm going to use this bracket notation, just clarify that. And from dispersive PD world, once you have a dispersive estimate, the next thing you typically do is try and prove what are known as Strickhart's estimates. So these are space-time integrated estimates, and beyond saying that you can prove them, I won't go into that. Okay, so now I want to go up to the nonlinear equation, And so, as we saw the other day in Alex's talk, a great first place to start is with the Duhamel formulation. And to first approximation, we expect our solution should look like a linear wave. And so what we're going to do is we're going to plug our linear wave into this nonlinear term, which gives us this second line. And now what we can do is try and naively prove energy estimates for this. So here, I'm going to assume my initial data is some Schwartz function. I'm going to assume that x, this norm, is some, say, Sobolev type space. I'm going to be very sloppy with derivatives and essentially ignore them. And so I can bound the linear part in x. And for the nonlinear part, I'm going to have one piece that I'm going to bound in L infinity and the other piece in this energy space x. And now what I can do is use the fact that I know that I should have 1 over t decay in L infinity. And so I'm going to replace this first L infinity bound by 1 over s here. And so I get So the first term is going to be of size epsilon, second term is going to be of size epsilon squared, but I'm going to have this integrated 1 over s factor, and again I'm being sloppy with time as well as derivatives. But the key point here is that I can't integrate this thing globally. This is only going to be of size epsilon up to some exponentially large time. And so this is only going to be small on what's called an almost global timescale, so this e to the 1 over epsilon, or constant over epsilon timescale. So in order to get to a global solution and be able to start asking things about asymptotic behavior, we need to look for some other structure sitting within the equation. So to do this, we're going to go back to the Duhamel formula, and this time I'm going to take a Fourier transform. So here I'm taking my f now to be, I'm going to take my solution, I'm going to pull it back by the linear group, and I'm now going to take the Fourier transform. And if I do that, I'll see this phase factor appearing at the top. And whenever this thing is non-zero or non-resonant, I can integrate by parts. I can put a time derivative onto one of the f's, and the time derivative of f is then going to be quadratic. So I'm going to take this quadratic nonlinearity and turn it into a cubic one by integrating by parts in time. So when can we do this? Well, we can do this whenever this phase function doesn't vanish. And in fact, a simple computation says that this can only happen when either one of the inputs or the output frequency vanishes. And so this is non-resonant. You only have trivial resonances. So in particular, as I said, you can integrate by parts in time and construct a normal form. And cubic nonlinearities should be better because we have more time decay. And so we should be able to integrate these in time and get globally bounded solutions. And another way of phrasing this non-resonance are what are known as bilinear Strickhartz estimates, which are simply the corresponding sort of integrated, space-time integrated estimates for products with linear waves. Okay, so this is by no means the only equation of this type with this kind of structure. And so now I want to jump slightly to what are known as the fractional KP2 equations. So here, this is a sort of another equation of this form. The key point is that if I stick alpha equals 2, I get out the usual KP2 equation. And if I take alpha equals 1, I get the infinite depth version of this Camassa-Choi. So this becomes the Hilbert transform times 2 derivatives. There are two very interesting symmetries all of these equations satisfy, and the Camassa-Choi certainly satisfies it. You have a scaling invariance, and you also have this Galilean invariance. So you can shift from a stationary frame into a moving frame. And so when looking for solutions to this equation, and all of these equations, I should say, have this same kind of non-resonant nonlinear structure, so they all, in principle, should be able to be solved by the same means. When looking for solutions, a good choice, or a natural choice of space, is to look for something that will preserve as many symmetries as possible. If we want to see interesting dynamics, we want to try and preserve symmetries, and so we want to look for the largest space possible, one that preserves the symmetries. And so this, the largest possible space or natural space that I'm aware of that preserves both the scaling and the Galilean invariance are what are known as the anisotropic Sobolev spaces. So it's a Sobolev space, it's L2 integrability in x and y, and you have some number of x derivatives, and the number is determined by the scaling. And so the important numbers to keep in mind are that for the KP2, this scale, or this number of derivatives is -1/2, and for the infinite depth Camassa-Choi, it should be 1/4. Okay, so when we first came to this equation, we thought, well, okay, this is basically the KP2, but we've changed the X dispersion a bit. Should be very straightforward to deal with. Reason being, we know how to deal with the KP2, have the same kind of structures. So back in 2009, there's work of Haddock, Hare, and Koch, where they are able to prove global existence and scattering for the KP2 equation in this space that preserves both of these symmetries. And all they did, so I say all they did, but it's an involved paper, but they proved a contraction mapping argument using linear and bilinear Strickhart's estimates that I mentioned already. And this was based on, I think it was Haddock's thesis, where he had showed previously that you have local well-poserness whenever alpha is bigger than 4/3. So remember, the Camassa Choi is alpha equals 1, and the KP2 is alpha equals 2. Interestingly, this is all of the mass subcritical cases. So the alpha equals 4/3 is when the scaling corresponds to actually the L2 norm itself. So we thought, well, OK, we'll just apply that method. Unfortunately, it doesn't work, and it doesn't work for a reason. My computer doesn't work either, for some reason. Unfortunately, this doesn't work for the Camassa Choi, and the reason is that these bilinear interactions are too strong. So there's a low-frequency, high-frequency interaction in this quadratic term, and the resonant interaction here is far too strong for the derivative in the nonlinearity to kill it. Another way to think of it is that this UUX acts as some kind of transport, and so the correct linear flow is not the constant coefficient flow, but something that's determined by the constant coefficient part and the low-frequency part of the solution. So it's a sort of a quasi-linear behavior creeping in. So we thought, well, OK, let's see if we can prove this. We were beaten to it by Linares, Pillard, and Sort, who showed that you have this kind of ill-poserness for alpha less than 4/3. And I should say here, ill-poserness is really in the sense of continuity of the solution map. It still might be possible to prove existence and uniqueness, but your solution map's certainly not going to be as smooth. And you can actually extend this to Bessel-type space refinements. And kind of the reason that we weren't completely surprised by this is you do have a similar issue in one dimension where the KdV is effectively semi-linear, but if you look at the dispersion generalized...
If the cube was long enough, make it straight, put it around the end of the...
Around the end of the thing, do you think, honestly? OK. You do have a similar issue in one dimension. So the KdV is semi-linear, but if you reduce the dispersion, you get these quasi-linear effects. So how are we going to get around this? And so, yeah. Sorry, in the... Oh, really?
Yeah, it goes back a long time.
But not in the critical space, right?
Not in the critical.
Right. I was just talking about the critical space. Thank you. Yeah, I mean, the KP2, I should say, is very well studied equation. And in fact, so the KP1, they will have huge literatures. Yeah. So how are we going to get around this? So let's go back to our linear waves again. So we want to try and kill off these low-high interactions. And one thing we could think about was what would happen if we would introduce some spatial localization. So I'm going to think about my function f as being some oscillatory factor times chi, where chi is your favorite bump function that's localized spatially near the origin. So this function f is now localized near the origin, and it's localized at some single fixed frequency. And now I'm going to plug this ansatz into my linear propagator, and I'm now going to replace the dispersion relation by its linearization about this frequency. And if I do that, I can then invert the Fourier transform, because this is now an invertible Fourier transform. We can write it out explicitly. And what we're going to see is we get some oscillatory factor times this bump function, but this bump function is now going to translate at the group velocity. And so the group velocity, of course, is given by the gradient of the dispersion relation. The key message here is that linear waves that are initially localized in phase space near the origin and at some fixed frequency are going to transport along a ray of the Hamiltonian flow, at least until they start dispersing. So why is this going to help us? So here's my cartoon. So here's some high-frequency wave packet, travels at some velocity. And if I have translation invariant data, I have I can't see that very well. So these colored blobs are meant to be my low-frequency wave packets, And if I have translation invariant data, I have lots of them. In particular, for all times, I have some of these bad low-high interactions occurring. So what happens then if I impose some sort of spatial localization? Well, I can throw away everything except for the one wave packet that starts off near the origin, right? Because my initial data was only localized there. In particular, we only get these bad interactions. Are we able to do something about this? Yeah. Okay. So we only have these bad low-high interactions for some fixed time, some short time. In particular, after we get past this sort of bad time, we should be able to get enough decay to close all the arguments. So, start. Okay. Okay. Yeah, that works. Okay. Okay, sorry about that. So, yeah, so if we introduce the spatial localization, we're going to kill off a bunch of these low-high interactions, and we're left with just one that happens only for a short time, and so in principle we should be able to deal with it. And so what's the theorem say? Well, the theorem says that, paraphrasing, if we have some small initial data in some space, and the space is, I'll write on the next slide, but it's largely unimportant. But the point is that we get solutions, they satisfy this 1/t linear time kind of decay, and what's more, they're going to scatter. Note that the scattering is in a sort of only in L2. We're unable to prove it in the full X space. So that's a sort of a drawback, I guess, of this kind of approach. How do we define this space X? So X is a weighted Sobolev space of some description. A kind of the useful or the interesting takeaway is that it's, number one, it's invariant under these Galilean shifts, so we're at least able to preserve one of the symmetries, and it imposes no moment conditions on the initial data. So one of the issues with working in things like the energy space is you typically have to assume that you, say, have mean zero functions. Similar spaces we used before in some work with Mihaila Ifrim and Daniel Tataru on the KP1. Finally, this solution scatters in the sense that I wrote on the previous slide, but it doesn't scatter in the usual sense. So typically, when you have a nice semi-linear equation, you expect if you apply the linear operator to your solution, it's going to be integrable in time. Now here we don't see any sort of logarithmic corrections to the scattering as you would see maybe in one dimension, but we certainly do have some modification in that we have to add some sort of normal form correction. Okay. Now, we're not quite the first people to look at this equation. Earlier this year, there was some work by Linares, Pilod, and Sort, where they considered local well-posedness and ill-posedness results in a variety of other topologies. And in particular, they look at the energy spaces. And one of the things that they are able to do that's nice is that they're able to rule out the existence of solitons. And so this is, of course, a well-known story for the KP equations, that the KP2 has line solitons but doesn't have nice localized solitons. And the same story is true here. We can't have we can't have localized solitons, but we can have line solitons. Okay. So for the last sort of 20 minutes or so, I want to give some sort of brief ideas from the proof, and I'm going to try and keep this as top level as possible. But yeah, I think we needed 4 derivatives, so it's not very sharp. I mean, this is So 1/4 would be the critical index, so we're quite a long way. So I want to try and indicate some of the broad brushstrokes of the proof, and without going into too many details, but I think there are some interesting ideas here that maybe can be applied in other contexts. So the first thing I'm going to do is only worry about the finite h, so finite depth, and I'm going to assume my depth is 1, and this can effectively be scaled out. And we're now going to run essentially a giant bootstrap estimate. So the local world poserness follows from standard arguments, and so I'm really going to focus on how do you get these global solutions. So the idea is that we assume that for some time we have a bound with this t to the minus 1 decay, and the bound's in terms of some constant m. And then we're going to show that if we assume we have this bound, we can actually improve it. So we can say replace this m by a half m. And then a continuity argument says, well, that means that, of course, we can then extend our solution a bit. And continuity arguments mean that at the time of existence must be the whole real line. Now, scattering is proved slightly differently. And in fact, scattering is really a corollary of the proof of global existence. As part of the proof, we determine these sort of point-wise decay estimates, and these can be applied to obtain scattering. Okay, so how do you actually prove the bootstrap estimate? So it's a sort of a three-step argument. The first step are energy estimates with sort of well-adapted operators. The second step are some point-wise bounds. So that's it. Not sure if it's my work that's unsupported or the computer. Okay, I'll try not to touch it too hard. Okay, take number 3. Okay, so first step is energy estimates. Second step is to try and do as well as we can with Sobolev embedding. So Sobolev embedding will get us so far, and usual energy method says use energy estimates, use Sobolev embedding. But this won't quite be enough to complete the argument, and this is because of this long-range behavior, this 1/t type decay. And so to get the sharp point-wise bounds, get these global solutions, we're going to use an ODE argument. So we're going to reduce it to a resonant ODE, and then we're going to show that, in fact, this ODE is OK. So this is where these several ways to skin a cat come in. There are a bunch of different approaches to step 3. And roughly speaking, there are 3 or 4, 5, depending on your point of view, approaches to this. But the key ones I want to mention are the spatial, or this is all for the cubic NLS at least, which was the kind of the easiest model in which to apply these things. So there are spatial type arguments. This is work of Lindblad and Soffer on the NLS. There are Fourier kind of arguments. This was work of Hayashi and Naokim and Kato and Pusateri, who really built upon the Germain Masmoudi-Chatin space-time resonances kind of technology. There are some other kind of more esoteric methods, inverse scattering transform, Dived Zhao, and semi-classical methods that Delors worked with. But the one I'm going to use is this wave packets idea that was developed by Mihaila Ifrim and Daniel Tataru. So the idea here is that the spatial arguments, you make some spatial ansatz for your solution, are extremely well adapted to nonlinear interactions. It's very easy to multiply things together in physical space. But the drawback of these spatial arguments is that they're not very well adapted to the linear parts. You're going to lose something in the estimates there. On the other side, the Fourier arguments are extremely well adapted, or indeed perfectly adapted to the linear part of the solution, because you can just get rid of the linear propagator by dividing by this phase function. The problem with the Fourier side is that you have to do a lot of work to handle the nonlinear terms. You have to do some careful decompositions and deal with these stationary phase kind of estimates. So the idea of this wave packet approach is to try and sort of interpolate between the two. We're going to try and work with things that have both spatial localization and frequency localization, and so they're going to be well adapted to both the nonlinear and the linear part. So That's essentially what I just said. And as an advert for this approach, it has worked very well so far for a number of other situations, such as this nonlinear Schrödinger equation, but also gravity waves, capillary waves, the MKDV, KP1, and so on and so forth. So it certainly seems to work quite well. Okay. So I think my grant money's going to have to buy a new computer. Okay, so try and briefly describe these steps without going into too many details. So energy estimates, I think probably everyone's very familiar with. You simply differentiate your energy, integrate by parts, and now what we're going to do, so here's the example with just taking a spatial derivative, differentiate with respect to time, and we can then, after integrating by parts, place one term in L infinity, get our t to the minus 1 decay out, and place the other terms into L2. And so here's our bootstrap assumption that we're using. So we're assuming that we have this t to the minus 1 decay. And now we can apply Gromwall's inequality, and this is going to give us an energy estimate with some small growth. But the key point here is that my constant m now only appears in the growth. It doesn't appear in the actual bound itself. And so I'm now going to run this argument with all of the kind of various parts of the norm I want to control, and eventually combining these, I'm going to get an identical estimate, but now for the whole norm. I should maybe mention here that this is perhaps one of the places that hidden technicalities creep in that for a lot of these energy estimates, you need to do some sort of normal form corrections to get rid of bad quadratic terms. So that's been sort of swept under the rug here. But the basic idea is we run some sort of energy estimates, and we end up with small growth of our energy norm. So step 2, I said, was to try and prove the pointwise decay just by using Sobolev embedding. And Sobolev embedding gets us quite a long way. So if we just run a Sobolev embedding, we're going to get this t to the minus 1 decay, and then a bound in terms of the energy norm. This works very well for times up to, say, time 1, but for large times we run into problem because our energy norm grows. So we have the decay we want, the 1 over t, but we have a small growth coming from this loss in the energy norm. So what we're going to do is we're going to use harmonic analyst's sort of favorite trick, is we're going to decompose our function. We're going to decompose it into a good piece and a bad piece that has structure. So this is a sort of, analogous to your Calderon-Siegmund decomposition in some way. So the idea is we decompose it. We call these parts the sort of the hyperbolic part and the elliptic part for various reasons. So the good piece is the elliptic part. It satisfies slightly better than 1 over t decay. So in particular, if epsilon is very small, this power here, minus 13 over 12 plus c m epsilon, is going to be integrable in time. And so I'm going to be able to get better than t to the minus 1 decay and close the bootstrap for this part. The bad part of this hyperbolic piece, so this satisfies this bad decay, where we just lose out on the t to the minus 1, but it does have the advantage that it's going to be localized in phase space. So what I mean by this is we know that for each frequency, if we start near the origin, we should be spatially localized along a ray of the Hamiltonian flow that I had earlier. And so these pieces are going to have this sort of micro-localization. They're localized in frequency and in space along the corresponding ray. Yeah. Okay, so it's going to remain then to try and get this pointwise decay for this bad piece. That's now our goal. So the good piece we can throw away, and we now want to deal with the bad piece. And so the idea here is we're going to use wave packets. What are wave packets? Well, I think most people know, but these are approximate linear solutions, and they're going to be localized on the scale of uncertainty in both physical and in frequency space. And the point here is that they're going to have the same localization as this hyperbolic piece. In particular, we can define this coefficient gamma, which is going to, by testing ux against a wave packet, and this in principle should measure exactly the size of the hyperbolic piece. So this wave packet, this psi v, is going to be localized in space along a ray of the Hamiltonian flow, and if we apply Planche-Jorel's theorem, it's also going to be localized in frequency, and so this should measure exactly the part of ux that's localized along a ray of the Hamiltonian flow and localized at a corresponding frequency. This is exactly the hyperbolic piece. And so the goal is then going to be to try and control gamma, and that in turn will tell us about this bad piece. How do you build wave packets? The point of this slide is not to be very explicit, well, it is explicit, but to illustrate that they're not very hard to build, essentially I can take my favorite compactly supported function, I localize it at some scales, which are these lambdas, and I multiply it by some phase function. And this phase function will satisfy the iconal equation associated to the linear operator. The key point I want to make on this slide is that my wave packet is localized in space at scales 1 over lambda z and 1 over lambda y in the two directions. And this z function, or z variable, I should emphasize this thing appears here. So remember, z is exactly what appeared in the fundamental solution. So it's localized at 1 over lambda z, 1 over lambda y in physical space, and at the inverse scales in frequency space. So this is localized exactly on the scale of uncertainty. And sort of the key to this argument is how do you choose these scales to be able to give you information about this hyperbolic piece for all times. So how do you choose a scale to give you, or to be a good linear solution on a time scale, say capital T? So it's going to be a good linear solution on a time scale capital T if when I hit it with the linear operator, the error looks like 1 over T. Another way to look at this is if we think back to this computation we did a while ago, where we replaced the dispersion relation by its linearization about a fixed frequency. If we look at the error between the dispersion relation and its linearization, then an equivalent statement to hitting it with a linear operator and getting 1 over T is that this error should also be like 1 over T. But this only needs to hold whenever we have the frequency localization of the wave packet. So whenever psi is very close to its base frequency and eta very close to its base frequency. And essentially a computation motivates a certain choice of scales, but the key idea here is that rather than trying to work on some fixed time scale, which we might want to do, is to try and choose these scales to be time dependent. So as time evolves, the scale of my wave packet is going to change, and this is perhaps best illustrated with a picture. So this is my picture. So the idea here is this red line is this ray of the Hamiltonian flow. This is a phase space illustration. So this z is a spatial variable, c is a frequency variable. And so I start off at time 1, localized at roughly order 1 in both physical and frequency space. And then as time goes on, this wave packet, this choice of localization, is going to shrink us more and more in the frequency direction. So we're going to get more and more focused on a single frequency. And it's going to dilate in the spatial direction. And so these wave packets in physical space are going to be growing. And essentially, asymptotically, it goes, or in some sense, it goes from these sort of spatial ideas to these sort of frequency localizations as time goes on. Okay. Okay, so we've now built this gamma function, and remember the point of this gamma function was to try and measure the size of this bad piece, right? We had this good piece that had good decay. We're now trying to control the size of the bad piece. And how do we bound it? Well, we simply differentiate it with respect to time. So we have two cases. The time derivative hits the wave packet, or possibly the time derivative hits the function, in which case we get a nonlinear term. So for the first piece, the linear part, we're going to use the fact that, in fact, our wave packet has some additional structure when you hit it with a linear operator, and you can integrate by parts and get additional decay. Perhaps the more interesting part is the nonlinear piece. And so the idea here is that, first of all, we can use the fact that we know that most of our energy is concentrated in this hyperbolic piece to throw away all the elliptic parts. So we throw away the good parts, and we're left with just the bad bit. But now we're going to appeal to the localization. By combining both the spatial localization with the frequency localization, we can actually show that this interaction is rapidly decaying. And it's essentially due to a mismatch of frequencies. Now, interestingly, there is absolutely nothing in this particular part of the argument that distinguishes between the KP1 and the KP2. So in principle, there's nothing, even though the KP1 has these very non-trivial resonances, at least in this part of the argument, there's nothing stopping us applying it to the KP1. So finally, we can complete the argument. How do we do it? Well, eventually we end up with some estimate, which is that the time derivative of gamma decays like so, t to some power that's ever so slightly bigger than 1, plus some constant times n times epsilon. And the point is we're going to choose epsilon very, very small, and if we do so, we can integrate gamma in time to get a uniform bound. But the uniform bound, crucially, is independent of m. We don't see m appearing. And so in particular, we can reconstruct this bad part from gamma and recover our sharp t to the minus 1 decay, because you'll see here that if we at least ignore the spatial factor, we have our t to the minus 1 and we have gamma. So provided the gamma is bounded, we get t to the minus 1 decay for the hyperbolic piece. So combining this with the estimate for the good piece, we get our t to the minus 1 decay, we close the bootstrap, and our solution exists globally. And then, as I said, the proof of scattering, essentially, we take these bounds, we take this good piece, bad piece decomposition, and we throw it in, construct a bilinear correction, and can show that you must scatter, in fact, to a linear way. Okay, so rather than giving any more details, I think that's more than enough, I want to finish by talking a little bit about some of the things that we could possibly do with this model. So one thing that came up in a comment that we had, we posted this on the archive on Monday, and I think by Monday evening we'd had a comment saying that we were very loose with our sort of very loose with saying this came from internal waves. Apparently there's no rigorous justification, so the Camassa-Choi argument is sort of a formal asymptotic expansion. And so one thing that would certainly be interesting to know is we now have some idea of what at least the dispersive part of this solution looks like, and be very interesting to know whether this really does describe something to do with internal waves. Another thing that would be very interesting, so we very much used a sort of a bazooka to kill a fly here. We've used some very heavy-duty technology to kill what, at least on the outside, looks like a fairly simple problem. And so it seems likely that our result is perhaps can be significantly improved. One thing that I'm very interested in is looking at other domains. So in particular, taking one direction to be periodic. I'm not sure exactly what the right one, as it were, from a sort of physical standpoint is. But there's some very interesting work about the nonlinear Schrödinger equation on tubular domains due to Hani, Pausauder, Tsvetkov, and Deschilia, who are able to show that when you restrict to having a torus, say, in one direction, or even a two torus, I think is the most interesting case in one direction, that the dynamics become wildly different, and in some sense much more interesting. Another obvious question with a KP model is, can we say anything about the line solitons and the asymptotic stability, perhaps, of line solitons? And in many ways, I think that's where some of these techniques are going now, is looking at the sort of the large data and looking at perturbations of solitons. And so some sort of initial work in that direction. For the 1D cubic NLS with the stationary potential, there are a number of works that I've put up here. And also there's some work on asymptotic stability of the NKDV near solitons, which is sort of a related problem. So these are related problems, but doing it in this context would be very interesting. And then sort of the final problem is, as I said, this came from an internal wave model, and at least as far as I'm aware, there hasn't actually been any work of this form looking at the full internal wave model. But in the 3D water wave case, and this is a very brief set of references, Alex's talk had a much more complete set of references, but at least for the water waves, we know for the gravity waves and the capillary waves, there are a number of results, and even gravity capillary, there are a number of results that give us these sort of global existence, the small data, and these sort of scattering results. And it would be a very interesting question to know whether the same kind of result that we're able to show for this toy model can then be proved for the full internal wave system. And so that's a good open question. Okay, so I think I'll stop there. Thank you all very much for your attention.
Thank you very much. Is there any question or comments?
So in the last part of your proof, on the back piece that you were looking at, so with your frequency space tiling, you had an inner product, so were you using also some kind of cancellation to look at the stability there, or you just?
So the inner product is essentially we're using a combination of the Fourier localization, but also we can use Poincaré's theorem and use the frequency localization. So the idea is that we have something that has phase space localization, and because we take an inner product, we must also have phase space localization of the thing we test against. That's the idea.
semi-linear or quasi-linear?
I mean, so it depends how you define these things, but it's a derivative semi-linear equation. But I mean, I've been told off for this, but I tend to think of these things more along what the correct linear behavior is. And I think if you were to look at the linearization of this equation, you wanted to get some useful information, you should really linearize about the solution itself, or at least about the low frequency part of it. So sort of paralinearization. So I would say it's a derivative semi-linear equation that has quasi-linear type behaviors. But people would feel free to disagree with me. The KP2, no, but this equation behaves more like the Benjamin-Ono, which I would say is a quasi-linear kind of equation. No? Okay.
Depends on the space, but if you work on nice spaces, it's semi-linear.
Okay, no, that's a fair comment.
Having lived a very sheltered life, I've never come across the fraction 97 over 96. So, you explain to me how that arises, please.
It's some power of 48. Essentially, you end up with, you can end up restricting your attention to a very narrow range of velocities that are determined by time, and at some points you have 1 minus some number of fractions multiplied together, and it happens, I think it's something like, I don't even remember exactly what it is, but there is something to do with a 12th and a quarter appearing, and so you end up with 96.
Any other question or comments? I have one question.
Yeah?
For my impressions that your equation is derived as asymptotic regime, long wave, and weakly nonlinear, and the y direction is weakly transversal.
Yeah.
So KP equation originally derived in order to investigate the stability of the line soliton in the perturbation from the transversal direction. So as you explained in the last slide, so it is natural to investigate the stability of the line soliton to the transversal perturbation. So, but maybe it's a future work.
Absolutely.
And, is there an existence theory for the line soliton? In the case of alpha is equal to, so it's the Benjamin-Ono equation, so it's okay. But in the general case, is there the existence theory for the line soliton?
So, I mean, one can construct, I think, line solitons by taking, I think the intermediate long wave equation has solitons, and you can then construct line solitons just by using that, right? And Galilean shift of it. So, but the answer is I don't know for sure, but my understanding is that these are known, at least existence. But there's absolutely nothing on stability as far as I'm aware.
Let's start to speak again.